Hello and welcome back to Math 100. This is section 2.5. This is the last section of chapter 2 before we go into chapter 3, which is on financial calculations, savings, and borrowing money. All right, but before we go to chapter 3, we have to finish chapter 2, and 2.5 is about very large and very small numbers. See, these very large numbers like billions and trillions are very hard for us to comprehend, even for mathematicians, right? So what we normally do is to compare these to something that we can relate to more easily. All right, so those are the things that we are going to be learning. All right, let's, as usual, share my screen and we will get started on section 2.5. Get your notes ready, and here we go. All right, section 2.5, about really big numbers and really small numbers, okay? And again, this is going to be a rather brief section. We have names for these large and small numbers. Let's go with something that we can handle, right? Now, we are going to be using this idea of called the order of magnitudes in some context. Sometimes it's called powers of 10. And so these are powers of 10, the 10 raised to these small numbers called exponents, all right? So when we say 10 to the third, for instance, all that means is you multiply 10 3 times. That's what that exponent is meaning, okay? And so 10 to the third power, or 10 to the third, is 10 times 10 times 10, which we know as 1,000, right? And so you notice here we have 3 zeros following leading 1. And so that number of zeros turns out to be exactly the exponent. So that's easy to remember. Okay, so here the exponents show the number of zeros following the leading 1. Okay, so that's the idea. And so that's not very difficult, right? I hope you know how to read this. 1, 0, 0, 0 is, of course, 1,000. Okay, 10 to the fourth would be 1, 0, 0, 0, 0, because you have to have 4 zeros. And typically we put a comma before the last 3 zeros. So this is what? This is 10,000. Okay, so we can handle so far. Right. How about 10 to the 6th? We skip 10 to the 5th. 10 to the 6th should have 6 zeros, right? And you may as well remember these large numbers. 10 to the 6th, 1 followed by 6 zeros has a special name, right? It's called a million. Right, that's what 10 to the 6th is. And then 10 to the 8th is going to have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 zeros. And then we can put commas going back, from the right. A comma should separate every group of 3 zeros. So you can see that right here, let's see, before the second comma, or before 2 commas here, you have 100. So this is read as 100 million. Okay, no problem here. 10 to the 9th has a special number. You notice here, every time the exponent increases by 3, we use a new name. And this is pretty typical at least in the Western hemisphere, in the Western languages. We had 1,000, we had a million, and then this is 1 followed by 9 zeros, and this is called a billion with a B, okay? So we have 1,000, a million, a billion, and 10 to the 12th has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 10, 11, 12, all right? So you have 12 zeros, and this has a new name. What is that? You have 1,000, a million, a billion, and a trillion. Okay. Now these numbers are in the news today just because after the COVID-19 crisis or pandemic, the government is spending a lot of money, and our budgets are in the trillions right now. Okay, now we also have these negative exponents. What do they mean? Well, 10 to the negative third, for instance, simply means 1 over 10 to the third. Okay, so the idea of a negative exponent, we don't have to go into a lot of details in this class. If you are taking an intermediate algebra class, for instance, we will be spending a lot more time studying the negative and positive exponents, but not in this class. All this negative sign means is it's 1 over something, right? So 10 to the negative third is 1 over 1,000, and this is 0.001, okay? And so how do you remember that? Well, if try to, and it is my practice, try to put this zero. See, sometimes people write 0.001, especially in America. I prefer that you write 0 point. This part I think is important. And this makes it easier to remember also. See, 0.001 or 0.001 has 3 zeros, right? If you include this 0 before the decimal point. So 0.001 has 3 zeros, just like this number indicates, okay? So that is probably a good way to remember that. Now, of course, this is the digits of the ones, and this is the tenths, and this is the hundredths, and this is the thousandths, right? So this makes sense that it is 1 over 1,000. It is 0.1% if you are calculating or converting this into a percentage. But the name we give to this number is 1,000th th ending. Okay, 1 out of 1,000. So it's 1,000th. And then 10 to the negative 5 would be 1 over 10 to the 5th, which should have 5 zeros. How do you read that? Well, this is 100,000, right? So this will be as a fraction 0.00001. Notice here I have to have 5 zeros, including that 0 preceding the decimal point. Okay, and this, because the denominator is 100,000, this is called a, oops, this is called a, oops, that's not what I wanted to get. And this is called a 100,000th. Okay, 100,000th. And that's what that number is. We will not spend a lot of time on these small numbers. We will probably spend more time on the large numbers. Now, we have prefixes in order to describe these numbers. Like, for instance, the word kilo, these are metric prefixes typically. A kilo just means 1,000, right? So if you have a kilowatt, for instance, it's 1,000 watts. Kilogram is 1,000 gram, and so on. And it's good if you remember these prefixes because they represent a particular number. A mega, okay, mega just doesn't mean something really big, like a mega store or a mega church or something, right? A mega precisely or specifically means a million, okay? And so when you say a megabyte, that's a million byte of data on computer language, in the computer language. Giga, no gaga, but giga is 1,000 times that. So it's 1 billion. Okay, a gigabyte is 1 billion byte, right? A terabyte is even more than that. It's 1,000 times a billion. What is 1,000 billion? It'll be 1 trillion. Okay, so we studied that, 1 trillion. This is, as we said before, it's 10 to the 12th. Okay, now in the smaller side, a milli is 1 out of 1,000. So it's 1,000th, okay? And you can also write this as 0.001. And so a millimeter is 1,000th of a meter. A micro is 1 over a million. And so should I write this? Yeah, 0 point, and because a million has 6 zeros, this should have 1, 2, 3, 4, 5, 6 zeros. So this is a millionth, and that's a micro. So a micrometer means 1 millionth of a meter. Nano is even smaller, and all of these go by, you have to add 3 zeros to this, right? So milli, micro, and nano. Okay, what is a nano? Nano would be So you had a thousandth, a millionth, and so this would be a billionth. And so it's 0.000, now 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Okay. I doubt that you would have to know these names for your tests and exams, but these are, things that may help you understand certain language, especially in computers and high-tech industry. Pico is what? It sounds like a name of a valley or a canyon in Santa Clarita. Now you have micro is a million, 1 over a million. Nano is a 1 over a billion. And then this is the next one, 1 over 1 trillion. So it's a trillion. Okay, so should I write this? Yeah, it's 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's ridiculous, right? Yeah, and you see, for these decimals, we can even put like commas. So it is, you have to count. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's pico. When do we use this, right? Well, for instance, a nanotechnology has to do with nanometer, and nanometer is 1 billionth of a meter. Okay, so technology is forcing us to use some of these prefixes. Okay, so in calculating these large numbers, calculating with these large numbers, it is good if you can eliminate or cancel unnecessary zeros, like when you are dividing. Right. So here's a question. Let's say if you have a $50 billion revenue, okay, $50 billion in taxes are collected. So the government has a $50 billion revenue, and it must be collected from 100 million people. If everybody equally pays, then how much would everybody have to pay? 50 billion should be paid by 100 million people. So the answer is, of course, 50 billion divided by 100 million, right? You say, well, these numbers are so big, I don't know how to calculate. Well, that's what I'm trying to teach you, okay? So you should know how to do these things. All right, so, and by the way, these are hard to do even on the calculators because you have to enter 5, 0, and then what, 9 zeros after that, divided by 1, 0, 0, followed by 6 zeros. So the point I'm trying to make here, cancellation, is trying to do it this way. The denominator is 100 million, right? How about the numerator? It's 50 billion, but 50 billion is 50,000 times million. You see that? 50 billion can be written as 50,000 million because 1 billion is 1,000 times a million. See, notice here you have millions and millions on top. Okay, you can cancel them. So this really comes down to 50,000 divided by 100. And you can cancel or divide both by 100. Basically, you're crossing out 2 extra zeros. Look, this is 500 over 1. You can do this in your head. The answer is $500 per person. Okay, it may not be obvious to you at the beginning. It's hard to guess when you have these very large numbers involved, but that's how you can calculate using cancellation, right? When you have large numbers on the top and on the bottom. So the answer is that each person has to pay $500 in order to raise or to come up with $50 billion in taxes. All right, let's go to the back side. We have just a couple of questions in the back, right? We talked about this already, so we don't have to go into details here, but let's say consider the size difference. How much is left when you spent $5.32 million out of a $45 billion budget? Okay, now remember, billions are so much bigger than millions. Who cares about 5 million when you talk about $45 billion? And I don't even care about the 0.32 million because these numbers are so small compared to the 45 billion. So what's the answer? Just like in the previous section, the answer is about 45 billion. You really haven't spent much at all when you have such a small number like 5 million compared to $45 billion. Okay, so the point is that these numbers even though they may look big, can be negligible in light of something much, much bigger. Okay, finally, let's do this last question. Try to make a comparison to understand big numbers. All right, the US population as of the most recent census is about 332 million people. If you can, now that's a lot of people, right? It really, see, we have a hard time understanding a number like 332 million. Okay, if you can count one person each second, let's say you know everybody's name in America and you call everybody by name. If you count one person or call one person's name each and every second, around the clock, every second, every minute, every hour, every day, you know, throughout the night, just all around the clock, 24/7. Every day, how many years would it take to count all these people? In other words, if you can count each person, one person every second around the clock, how many days, how many years would it take to call everybody's name? Okay, that's the question. So how do we do this? Well, we have 332 million people, right? And you know, we can do a unit analysis, I guess, right? So this is people. And what we're trying to do is we're trying to call them one person per second. You know, it's a little tricky to do analysis. So if you want to ignore the units, that's okay. It's one person per second. Right? Well, you know that we have 60 seconds to a minute. How do you, by the way, how do you know which one goes on top and which one goes on the bottom? Okay, so this is a little tricky, as I said before. The second is in the denominator of the denominator, so I want to cancel this. And besides, we want the number to be smaller, so you know you have to divide this very large number by, you know, numbers that are rather large. So 1 minute over 60 seconds. Remember, this represents 1. And so we get to divide by 60. And this will tell us how many minutes it will take to calculate or to count these many people. Okay. So the answer is we need to have 330 million. Maybe it's easier if I just say 330. So how many seconds would it take? That's an easy question. All right, so let me go ahead and rewrite this. Yeah, so let me go ahead and write it this way. It's clear that all we need is 332 million seconds, right? Because that's how long it takes to call everybody's name if it's one person per second. So the question really is, how many days is 332 million seconds, right? So I'm going to divide it by 60 first to find the number of minutes, and then 1 minute, oh, sorry. Yeah, that's right. And then 1 hour consists of 60 minutes. And then 24. Let's go ahead and do 1 day. Consists of 24 hours. Again, all I'm doing is multiplying by a bunch of ones, right? Because 1 day over 24 hours is precisely the 1. It's the numerator and the denominator are the same. And then you have 365 days, and that should go in the denominator. And 1 year is 365 days. And again, if you are not concerned about, if you want to just calculate this without worrying about the units, I think that's doable because it's rather simple that, you know, all of these will cancel. So the answer, the only thing that's going to be left is the number of years. All right, and so that is what we will come up with. It's basically 332 million divided by 60 times 24 times 365. The denominator represents the number of seconds in 1 year. All right, so then this is the answer. I mean, what you have to do is to do 332, 0, 0, 0, 0, 0, 0. There's nothing to cancel at this point, right? And then in the denominator, you have to just find this product first. On the calculator, if you know how to use parentheses, that's easier. Otherwise, you may want to find the denominator first, 60 times 60 times 24 times 365. That is the number of seconds in the year, and divide 332,000,000 by that product. Okay, and the answer turns out to be about 10.5. Okay, so the answer to this question, although it seems to be very large and it's hard to estimate it in advance, is about 10.5 years. That's how long it takes to call everybody's name or to count each person, if you can count one person every second around the clock. Okay. See, the point is this makes it a little more understandable. I mean, it makes it a little more comprehensible for us. When somebody says 332 million, it doesn't make a lot of sense, but now it does make a little better sense, right? The same answer is, we will have the same answer if somebody asked, if you have $332 million all in a dollar bill, you know, like, and if you can count $1 bill each time, each second, how long would it take you to count $332 million? And the answer is, well, it's going to take you about 10.5 years. And that sort of gives us an idea, a concrete idea of how big this number is. Okay, so that's the whole idea. Learn to work with these large numbers. You don't have to necessarily memorize all of these prefixes, but learn not to be intimidated by very large numbers. Okay, so this wraps up chapter 2. Congratulations, and I hope you have learned enough and for chapter 2, and I will see you when we go into chapter 3. Have a great day. Take care.